This chart tracks performance on a complex task, replicating machine learning research. A 27 billion parameter model named Faraday achieves a score of 0.856, outperforming both Claude Opus 4.8 at 0.828 and the massive Codex GPT 5.5 at 0.796. Faraday achieved this margin by operating as a director. It dictates the experimental logic and orders a model roughly 200 times its size to write the boilerplate software. The failure of much larger frontier models on this task stems from how the problem is structured. Replicating a published paper demands active research rather than clerical copying. Because a paper is a lossy compression of the work behind it, a model must fill in the missing experimental details through hypothesis-driven exploration. This environment breaks standard reinforcement learning. Most RL systems rely on perfectly verifiable rewards, like passing a unit test or winning a game of chess. Paper replication has no objective test to pass. Training in a domain where success cannot be mathematically verified required a specific four-part stack: an auto-generated task space, an llm-judge validated against humans, a nested agent architecture, and a stabilized GRPO recipe. Establishing a model's ability to navigate the ambiguity of replication serves as a prerequisite for more open-ended scientific tasks. To train a model using reinforcement learning, you first need a highly scalable environment to train inside. That requirement led to the creation of the Replica task space. A vision language model scans 100 published papers, redacts the results figures, and locks the original plots away. The agent then receives the redacted paper and strict constraints: exactly 60 minutes, and a 1/7 slice of an H200 GPU. These compute and time limits are an intentional bottleneck. They guarantee that the original experiment described in the paper cannot simply be rerun natively. Because the full run is impossible, the prompt forces the agent to design and execute a faithful scale-down of the original experiment, deciding exactly which parameters to cut, fewer epochs, smaller batches, or narrower searches, without destroying the core scientific claim, forces the model to exercise scientific judgment. By strictly constraining hardware resources, the Replica dataset shifts the agent's primary challenge from raw coding efficiency to scientific prioritization. Evaluating a replicated paper by checking for a pixel-perfect image match fails. It rewards cosmetic formatting over the accuracy of the underlying experiment. Claude Opus 4.7 acts as a rubric generator, creating a grading rubric while completely blind to the original gold plot. The rubric flows only to the judge node. Hiding the plot prevents cosmetic overfitting, and hiding the rubric prevents the agent from gaming criteria. The judge itself is Codex GPT 5.5, and its access is massive. It receives the redacted paper, the agent's code, the entire Git history, and the goal plot, and the ability to re-execute the agent's code to test its claims. This chart visualizes the validity of the reward signal. The rubric judge achieves a Kendall-Tau self-agreement score of 0.66. For context, PhD-level humans only agree with each other at 0.30. Minimizing judge noise and human variance is the prerequisite to converting subjective scientific evaluation into a stable mathematical reward signal for RL. Traditional multi-agent systems attempt to conduct science by relying on complex, hard-coded harnesses where models role-play different researchers. Faraday discards this. Its harness is a linear, append-only history equipped with exactly 5 functional tools: apply patch, read file, list directory, grep files, and shell. This minimal interface enables the core architectural paradigm of the system, coding agent as tool, or CAT. Faraday uses its shell tool to spin up a command line instance of a massive codex model. This creates a strict division of labor. The 27 billion parameter model acts as the lead researcher. It dictates the logic, scopes the experiments to fit the compute budget, and checks the results. The 5 trillion parameter model acts strictly as the executor. It writes the actual boilerplate code and handles the software engineering implementation. This separation of scientific judgment from software engineering execution allowed the 27B model to direct a 5T model with a measurable performance gain over the larger model alone. If you apply standard reinforcement learning to a 1-hour, 500-turn task scored by a noisy LLM judge, the training collapses. In standard group relative policy optimization, or GRPO, Judge noise directly corrupts the group relative advantage. It punishes the model randomly. This equation illustrates the first fix. The system averages 3 independent judge samples for the final reward. This mathematical step cuts the variance of the noise by 3. The second major bottleneck of long horizon RL is credit dilution. Over a 500-turn rollout, the credit for a good decision gets diluted across hundreds of irrelevant coding steps. To counter this, the judge emits turn-level credit weights. It assigns higher mathematical value to the specific turns where critical scientific decisions or delegations to the coder were made. The weights are normalized so the weighted token sum exactly equals the raw token sum. It redistributes credit without inflating the total magnitude. Without this exact turn-level normalization constraint, the training completely collapses in roughly 50 steps. This specific method of distributing credit allowed the policy to improve over long horizons, where standard reinforcement learning failed to maintain stability. When researchers applied 24 rounds of extensive prompt optimization to the baseline models, they hit a hard performance ceiling of 0.802. Prompting alone cannot match Faraday's score of 0.856. The baseline models effectively cheat the prompt. They opt to hard code expected outputs or hand-populate data libraries just to generate a plot that visually looks correct. Faraday actually builds the underlying mechanisms. When tested, it runs real skill acquisition phases and constructs genuine evolutionary search structures. For the GNOME task, Faraday runs 5 distinct seeds and maps the statistical spread. The baselines rely on a single, unsupported seed. Because the rubric-judge explicitly rewarded faithful scale-downs, Faraday learned intrinsic scientific integrity over superficial metric hacking. Decoupling judgment from execution yields an immediate capability implication, instant composability. By simply swapping the underlying coder tool from a mini-model to GPT 5.5 at runtime, Faraday's score instantly jumps from 0.662 to 0.740 with 0 retraining. The authors detail honest caveats. Absolute human-to-judge agreement is still low at 0.19, and the reward pipeline remains noisy. High-level scientific judgment is a trainable layer, while raw code execution is merely a rentable commodity. While replicating existing papers is a constrained starting point, it demonstrates a method for training agents on underspecified research tasks.